This is about security of smart contracts. And I hope that you will learn a few things about how to make your CorDapp more secure, and also a few new interesting things about blockchain security in general. This is our agenda for today. First, we'll take a look at some real-life hacks that happened on Ethereum smart contracts, just to get a feel of what happened in real life. Next section will be about blockchain designs and security characteristics, but I realized this morning that time is a bit short, so we'll just race through this section. And the last bit is around Corda and what you might find unintuitive and what you can do to stay out of trouble. So we've all seen headlines like this in the past few years. $60 million theft, $32 million theft. Now, this being DevDay, let's look at a few of these hacks so we understand what can happen out there. And first, let's start with a crash course in Solidity and Ethereum. So it's very few things you need to know. It's just that Solidity is an object-oriented language with a JavaScript-like syntax. A smart contract in Ethereum is just an object that has states and methods. Methods have visibility modifiers, same as in Java. Once they get deployed, they receive an address, and the contracts get replicated on the network. And also they can send messages to each other, so they work with other contracts. And also there is a fallback method that gets called when someone pays money into a contract. And this was used maliciously a lot. OK, so let's look at the DAO hack, which was the first one. So what happened here is that an attacker just deposited some money initially into the contract and then withdrew it. Actually called a function to withdraw it, which was a function called splitDAO. Now this function, simplified, was fairly straightforward. First thing it did, it verified the balance, which was OK because this contract had some money. And then it transferred the Ether into the evil contract. But the fallback function was malicious in this case, so we just called into the splitDAO function again before it gave us a chance to update the balance. This is called the reentrancy problem. So it was able to withdraw again and again and again until he withdrew like $60 million. And only then he allowed it to finish and update the balance. And the fix is just really simple. It's just moving the line that updates the balance to before the payment. And that fixes a bug. So that cost a lot of money. The next one we'll look at it is the Parity Multi-signature wallet library. There were two hacks on this library. The first hack was quite simple. So this library had a function called init multi-owned, which the developers left without a visibility modifier. So by default, it was public. I guess I didn't expect that. So it was supposed to only be called from the constructor because it sets the owner of the contract. So an attacker noticed this and made himself owner of 3 contracts on the Ethereum blockchain that had ICOs at that moment. So by being owner, he was able to drain all their funds and steal $32 million, just a visibility modifier. One we look at is the second hack on the Parity wallet. This time, the attacker just killed the library. So the library was deployed as a contract and was left uninitialized by the developers because there were no funds in it. So probably they didn't think about it. So someone just made himself owner of the library. And because he was owner, he could kill it. So this person froze everyone's wallets, which caused like $500,000 Ether frozen, $100 million in today's value. What lessons did they learn from this? Well, by reading the postmortems, most of them blame the unintuitive quirks in the Solidity language and the EVM for these attacks. And that's quite right. And some of them even admit that the exploits, even with more auditing, wouldn't have been obvious. So that's it. My personal opinion is that the second cause for the magnitude of these bugs was the actual design of Ethereum itself. And we'll look in the next section on why that mattered. Blockchains, like any software, have to make design decisions based on trade-offs and benefits. And we'll look at Corda and Ethereum and how they made different decisions and what security impacts this has. Not other impact, just security impacts. Okay, so first difference is that Corda is a private blockchain while Ethereum is a public blockchain. A private blockchain means that everyone is verified and everyone is an identity. In Corda, they receive a certificate, so everyone is known. In a public blockchain, everyone is anonymous and you don't know who you're talking to. Now, what I'm saying is that any meaningful attack on a private blockchain will be traced to a real identity because everyone is known. So that's a deterrent, because if you do something malicious, people will know. In a public blockchain, if you hide behind proxies, no one will know, and attacks will happen, and they did happen. The next big difference is how transactions get broadcast. So in Bitcoin and Ethereum, all transactions are broadcast to everyone, while in Corda, they are kept private between peers. There's many implications of this, but from a security point of view, if a hacker finds a vulnerability in a smart contract, in Corda, he can just steal the states he knows. There's no way to steal stuff he doesn't know. So if he didn't have business with different banks, he can't steal stuff from peers he didn't have business with. The next big difference is in the record-keeping model. So Bitcoin and Corda use the UTXO model, while Ethereum uses the account model, account and balance. Now we've seen that the accounts and balance is very simple. It's just objects and states, so everything is familiar. But it is very hard to get secure because it's very sensitive to order. We've seen in the DAO Hack that just the order of statements made a huge difference in the security of the contract. The UTXO model is a more functional approach because each transaction is a transition between immutable states, input and output states. So the order doesn't matter in this case. So it's easier to reason about security. And the final difference is that Ethereum built their own execution environment and languages, which was a lot of fun probably, but it had in hindsight, it had some consequences. It wasn't the most pragmatic choice. A short conclusion, CorDapps are less likely to get hacked because the network is private and everyone is known. Corda is more forgiving to mistakes because transactions are private and you cannot steal what you don't see. Corda has a more secure programming model because it's based on the functional UTXO style. And it's also based on the JVM and Java or Kotlin, which are more well known to the community. Some unintuitive aspects of Corda itself, especially if you're coming from a traditional centralized programming background. So we'll see why you shouldn't trust Java class names. We'll see why you should always check your dependencies. And we'll see why you should avoid unexpected attachments in your transactions. Okay, to understand why these are necessary, let's take a step back and look at the main guarantee of Corda, which is that once a transaction verifies, it should always verify on any node, any version, any time. Now, if you think about it, this is fundamental because if it were false, transactions couldn't be final. So we need to achieve this statement. So there's three items that need to be achieved. First, transactions must be immutable, which is fairly obvious, and they are by construction. The UTXO model ensures that. A second point is that they must always be verified with the same code. Otherwise, if the code changes, of course, the result might be different. And they must be run in a deterministic sandbox, which means that if they somehow use any sort of time or random function, they might return a different result, which is not good. It violates the guarantee. So they must run in the deterministic sandbox. Now, we'll take a look at the second point that has all the implications we mentioned before. OK, so it's time for a short quiz on transaction verification in Corda. It starts very simple. First question is, how do you execute code in Java in general? By using class loaders. Of course, loading a class in a class loader and just running it, which is what we do for transactions. A second question is, what code do you have to run to verify a transaction? Well, of course, a smart contract code for all the contracts of the transaction. Fairly obvious. A third question is, where do you get this code from? But in Corda, transactions contain both data and code. So the transaction contains a list of attachments, an attachment being just a jar file with code. So you take the code from the attachments of the transaction. And the last question, which is a trick question, is how do we know if the code is legitimate? If anyone in Corda can build transactions, how do we ensure that this code is actually what was intended to be? So this is where contract constraints come in, which you might have heard about. OK, so let's drill a bit into contract constraints. This is one of the areas which I find most confusing about Corda. So we've seen there are a mechanism to ensure that smart contract code is legitimate. That's for sure. But to understand what exactly is the problem, let's take a step back and look at this Java class name. Now, in a normal Java program, when you see a class name like an object of this type, a mega token, you know exactly what it is. You can just use it. There's no second thought. But in a decentralized system such as Corda, where code and data travel together, anyone can compile a class name and build a jar file and distribute it together with the objects. So you no longer have the guarantee of if you see a class name, you know what it is. It can be anything. So that's why we came up with the contract constraint concept, which is like a second cryptographic coordinate for smart contracts. So for example, one possibility is to use the hash of the jar file as the root. So you know a hash, it travels with the states. You know the hash, you know the class name. This forms the address of the smart contract. And the more flexible one is the public key of a signer. So if Megacore signs a jar containing megatoken, then states can just hardcode the public key of Megacore, and then you know the identity of this class. So this ensures basically another way to look at it is a contract constraint is a second cryptographic coordinate necessary to identify a contract, a smart contract address. Now, we'll actually look at an example to understand even better how it works. So just a normal Corda transaction, swapping tokens for bonds. Nothing special. We see that states contain both a contract and a constraint. So they travel inside the states, and they form the smart contract address. So we have in the states contain both the data, which is Alice owns 5,000 tokens, and the smart contracts that governs this data. We notice that the smart contract address must propagate to the output states belonging to the same smart contract. And now to make this transaction verifiable, we need to add code to it, because now it just contains data. So we need to add the megatoken jar, but which needs to be signed by Megacore to satisfy the signature constraint of that state. Same for the bond. And to make things a bit more interesting, let's say that megatoken depends on a token's SDK, and it needs an abstract token to run, so it extends abstract token. So in order to be able to verify this transaction, we need to add this as well. Otherwise, we'll get class not found exceptions. So we need all three attachments. So what happens next? Well, Corda will identify which states and which contracts form the same smart contract, and will verify the constraints. So it will do that for the tokens. It will do that for the bond. And we see that for the abstract token, the dependency, there's no check. So it falls into the so megatoken must do that, because otherwise no one will do for now. And we'll see what happens if you don't next. So next step for verification is Corda builds a class loader of all these attachments. And now megatoken can verify that abstract token is its dependency inside the verify method. So megatoken, now we can run the megatoken verify functionality. We run the bond verify, and the transaction is valid. OK. So let's see what happens if megatoken doesn't check its dependencies. And an attacker like Chuck knows about this. And he will attempt to exploit it by inventing tokens, basically. So what he can do is Chuck can just attach his own version of the abstract token jar because no one verifies it. So he attaches his own version, which doesn't check that input equals output. So he's able to build a valid transaction by exploiting this vulnerability in the mega token contract. So the conclusion is that you must check your dependencies in the verify method, basically by checking that the hash or the signer of them is valid. And you must remember that only the main contract jar is checked by the platform, not the dependencies. OK, well, yeah. So in Corda 4, there's an additional check about trusting jars. That would prevent this attack, but it's not a check that's relevant. It's just you couldn't attack Corda this way for now. Let's look at this other transaction. Same tokens for bonds. But if you can spot something unusual here is that these are fake bonds. So Alice didn't check the constraint of that class before signing this transaction. So she spent her tokens on fake bonds. So remember, the address is a class name plus constraint. If you don't check the constraint, anyone can create that class name and create states and distribute them. So you must always check both when you sign transactions. So never trust just the class name. Also check the constraint for the full smart contract address. You must do that when signing transactions. You can do that when running Vault queries. There's a new API. And also in your contract code, when using another contract and there's other states, you must check the constraint of those states. Otherwise, you risk what Alice did. And there is an alternative technique called package ownership that makes this a bit easier, but there's no time to discuss it now. OK, so the final attack, which is a bit hypothetical, but who knows? Strange things happen. So let's assume that mega token is doing everything right, checking dependencies, but it has some dynamic behavior, like a service or something that's loaded dynamically from the class loader. Now what an attacker can do to exploit it is to attach an evil jar that just manages to inject this service or do something evil. We don't know yet what, but who knows? Something might happen, and he might be able to build a valid transaction just by injecting an evil jar. So the lesson is that check that attachments contain nothing unexpected. You can do that because you have access to the ledger transaction attachments field. So you can check that it's only your jar and the jar of the contract you want to exchange with. So you can whitelist what you know is safe. And this is because all attachments are added into a single class loader. And that might be a cause of some attacks. Corda has a no overlap rule, which means that an attacker cannot override your class name. But there's other behaviors that might happen. So, conclusion, always check your dependencies, always check your constraints. You can start in Corda with restrictive rules, like not allowing, if you know that your CorDapp doesn't work with other CorDapps, it's only used inside a specific context, you can just hardcode that in the contract. There's no problem. I just allow these 3 attachments, and that's it. And you can, in the next version of your CorDapp, you can relax it, whitelist more attachments, and so on. You can do that because the signature constraint allows you to evolve your CorDapp. And that's fine. And Corda itself, we're working on dependencies, we're working on class loaders, so all these areas will get better. So we might relax the rules even more. Thank you, everyone.